Hello, Mark Palmquist. Today I'm going to do a video on riding moment, but I'm going to be comparing the riding moment of a keelboat, the Cape Dory Typhoon Weekender, the Sunfish, the Laser, the Hobie 16 Catamaran, 49er Skiff. Pair that with the Wingmaran, and then we're going to look at the windsurfing boards and kite surfing boards as well. So I'm going to go through several boats, starting with the Cape Dory Typhoon, which is a small keel boat, which we actually had for 3 seasons. Riding moment is created when you have a distance, a lateral distance between the center of lift and the center of mass. Okay, so once you get going and the boat starts to heel, the lift is from the area of submerged volume. So it comes from the center of the area. This is the center here, and then there's a distance opens up, a lateral distance between the center of mass. Okay, so the center of mass of a keelboat is divided into 2 things. It's the actual hull, which is somewhere in the middle, and then the lead weight on the keel. In the case of the Typhoon, it's a 2,000-pound boat and 900 pounds are in the keel. So if you take the average between these two, the average is right in the middle. So somewhere between here and here is the center of mass of the boat. And I just threw in an extra 100 kilograms for 1 person and some gear. Okay, so you only get a distance of 23 inches, but because the forces are so high, the weight here is 1,100 kilograms, and the buoyancy lift and these 2 forces are equal and opposite, and it's this distance that allows the sail force to not capsize the boat. So if you multiply these 2 together, the weight, the force times the distance, you get a riding moment, which is 660, and the sail area is 160 square feet. And so I did this ratio, and I put sail area divided by riding moment, and I got 0.24. So this is a very low number. This indicates that the Typhoon it would be extremely hard to capsize. And that is actually the case. It's almost impossible to capsize a Cape Dory Typhoon, and so that's why they use it as a training boat. Okay, let's go on to the next couple boats here. I have some very popular boats, small boats, that are very popular in the United States, and the Laser is very popular everywhere. So in this case, if you remember, the distance arm of the keelboat was only 23 inches. In this case, if you hike out and you get your weight way over here, the weight of the boat is here, and the weight of the person, the crew, is here, and then you look at the percentage of these 2. The boat is 55 kilograms and the weight of the person is 80. So this dot is a little bit closer to here than it is to there. And I did this all on my CAD system, so this is very accurate. And then I kind of estimated the submerged volume, and I took the centroid of the submerged volume, and that's where you get the center of lift, and you get 29 inches. These boats go, the Sunfish goes about 10 knots max, and the Laser can go 11 or 12. It's a little bit more of a planing hull, and it has a little bit better sail, but both sails are about 75 square feet. The Laser has like 76 square feet, but it's a more powerful rig. So I did the same thing. I took the weight, and then the distance from that to the pivot point, which is here. The pivot point is always the center of lift. And so you get 98.5, and then the sail area is 75, and then you divide the sail area by the riding moment, and you get a really big number here. And this is why sunfish, you can end up capsizing quite often on a sunfish and a laser. They have a relatively large sail area for their size. Okay, another interesting thing to note about this is 55 kilograms is actually now pretty heavy. There are some newer, lighter sailing dinghies, and some of them go up to 15 knots. So, so the weight of the boat does affect the top speed of the boat in this case. That's always the case, actually. Okay, let's go to the Hobie 16. This is probably one of the most popular beach cats of all times. The weight of the Hobie 16 is 150 kilograms. And if you have one person on a trapeze, this is all drawn to scale, by the way. And I'm just assuming the weight here is around the belly button is 80 kilograms. And then you take the proportion of this, and the sum total is here. It's closer to here than it is to there because this number is bigger than that number. So the distance here is 68 inches, and the top speed of a Hobie 16 is between 18 and 24 knots. Now you'll notice that the riding moment is 395, and then if we go back to this, the riding moment is 660, but the top speed of this boat is 6 knots, and there's a couple reasons for this. The major factor in its riding moment is its weight, not its distance. So if you want to go really fast, you use less weight, but you use a greater distance. So in other words, if you wanted this monohull to go faster, you would increase the length of the keel, and you would move this weight down here. You'd get a greater distance, and whatever that increase is, then you would take that off the weight. So you could if you double the moment arm by having a longer keel, you can cut a good 50% off of this the weight here, and you'll have the same riding moment, but you'll have a lighter boat. And this boat, the water line would go down, and you'd have less surface area drag here. This is frontal area. So one of the reasons that monohulls are so slow is because they have a lot of cross-sectional area under the water. So the other thing that you can do to a monohull is you can add, some kind of a DDS, dynamic stability systems wing or whatever, and this creates some lift here, and then the center of lift is somewhere between the two, so it moves the center of lift somewhere here, and then you get more distance. If you have dynamic lift here and you have buoyancy lift here, and you add these together, your sum total is going to be somewhere in between the two, and so that's a greater distance. So then your distance is a lot bigger, and that's the other way to do it is to make the hull wider. So now you look at the hulls of these ocean-going monohulls, and they're a lot wider, and they're a lot lighter, and they're flatter, and the hull can hydroplane. So those are 3 things that you can do to a monohull to make it faster. So what you're doing is you're exchanging weight for distance. Okay, so because you're kind of doing that here. You're exchanging weight for distance on a catamaran, especially if you have a trapeze. This distance gets really big. You get bigger speeds. The other thing is the cross-sectional area of this is relatively small compared to the monohull that weighs 2,000 pounds. This only weighs 230 kilograms total. So, so that is why you can get higher speeds with a catamaran. Okay, now let's look at windsurfers and kite surfers. These are almost the same. You have a very light board. You're leaning your weight to windward. You're canting the sail a little bit. I don't know what these actual angles are. If you watch videos, it seems like the kite surfers are now leaning even further to windward, so this angle might be a little bit steeper than that. But you still have the same physics going on. You have the center of lift of the sail is up here. On a kite surfer, it goes right through your arms. So potentially a kite surfer could end up being faster than a windsurfer, even though these distances are pretty much the same. Actually, lately, I actually saw somebody stick a lifting foil like this on a kite surfer, and then that moved the center of lift further, and they got a bigger distance. So whatever that was, it created a larger distance arm here between the center of lift and the center of weight. And but anyway, the top speeds of both of these are about the same. This is around 55 knots, and this is around, I think the top is now 56 for a kite surfer, 56 knots. But the interesting thing to notice about this is, okay, let's compare. This is really interesting. Okay, here's a laser Sunfish, 29 inches, 34 inches. These are almost the same, right? This might be a little bit higher. But what is the major difference here? The weight of this boat is 55 kilograms, and the weight of this boat is 15 kilograms. This one is semi-planing, and this one is fully planing. So the weight of the boat has a big effect on the speed, and whether or not it's a fully planing or semi-planing also has an effect. All right, so that's about all I can say about this. It's interesting here, the riding moment. If you do the same math, you take the weight, the total weight, and multiply it by the distance in meters, you get 78, and then the sail area is about 65. That's average for a windsurfer. And then here you get a sail area to riding moment of 0.83, which is really high. And I don't know the sail area of the kite surfer that broke the speed record. It's not listed anywhere. I could not find it. If anybody knows how big the sail area is of this kite that beat the record, somebody please tell me in the comments, because I just have a big question mark there. The string on a kite surfer is very long, and it's an inflated sail, so I don't really know how the drag characteristics of this sail plus this long kite string compare with a windsurfer. But since they have very similar moment arms, very similar weights, and very similar speeds, I would assume that the sails basically are quite equal as far as their effect on the speed. This actually might be bigger, but the drag here might kind of like, the drag on this long line might sort of balance it out somehow. I don't really know. In fact, I bet if they put some kind of aerodynamic fairing on the kite string, they would be able to get faster speeds. Okay, I could go on and on and on. Okay, so here, this is a 49er skiff, and it's from wing to wing, it's 9 foot wide. And here's the weight, it's 122 kilograms. You have 2 people this time on a trapeze, not one. So this is where the total center of weight ends up being, and this is the displaced water centroid right here. So this is the center of lift. This is a planing hull, and here you have a distance of 63, which is interesting because it's almost as much as a Hobie 16. It's just a little bit less. But, okay, also the Hobie 16 goes 1.3 times the speed of the wind, but this boat goes 1.5 times the speed of the wind. And so why is this able to go 1.5 times and the Hobie 16 can only go 1.3 times the speed of the wind? I think it has to do with the fact that this is a planing hull as opposed to a displacement hull. Planing hulls are always faster than displacement hulls once you get over a certain speed. And I don't know what that speed is, but considering the fact that this goes 25 knots and the Hobie 16 goes about 24 or 25 knots max, I would assume that the crossover point is somewhere just below 25 knots. Between the speed at which the planing hull gains an advantage. So anyway, this is kind of like, if you analyze this, it's kind of like a windsurfer, except the guy has longer arms. So imagine your arms are now this long, so you're able to put your weight way over here. Okay, so let's look at this number here at the bottom. The riding moment is 435, which is slightly more than the Hobie 16. And the sail area is 228, which is about the same as the Hobie 16. The sail area to the riding moment is 0.52. So what that means is you're probably going to be capsizing just a little bit more on a Hobie 16 than on this boat, but both of them will probably capsize at some point. Okay, here's a Wingmaran. Now this is not the fastest version of the Wingmaran. This is just the one that I have designed. You can make the wings longer and you can make it faster. You can put a bigger sail rig on it. But my dad was able to reach 1.5 times the speed of the wind, which is the same as the 49er. So let's look at the forces here. The weight of this boat is 80 kilograms. The weight of the sailor is 80 kilograms. So this dot is exactly 50% from here to there. It's right there. Oh, wait a minute. I drew this wrong, didn't I? Yeah. Okay, so I'll have to edit this and redo it. I don't know what that distance is. I don't have my CAD program here. Okay, let's just assume that that I add a trapeze line to this boat. Then the guy would be over here, and this dot would be here, and then this dot would be here. So let's just assume that I add a trapeze to my boat, just like this one has a trapeze. This guy has 9-foot wings. Mine are only 5. But because I have a wing, this pushes the center of lift further out. This one is still under the hull. It's right here. This one is between these 2 hulls. So in the case of the Wingmaran, you have 2 hulls. You have the main hull, which is mostly a displacement, but it's also semi-planing. And then you have the ideal planing surface on the wing. Now, you'll notice that this volume looks like it's holding more weight, but even though this has less submerged volume, it creates more of a hole behind the wing, and that hole contributes to the lift. So you have dynamic lift here, and you have semi-dynamic lift here, and I'm assuming that 66% of the lift is being carried by the wing, and only 33% is carried by the hull. And then that's how you come up with this dot, which is somewhere between the two. And you get the same number here. Now the difference between these two boats is the weight. This boat is much heavier. So I did a calculation. I don't know what the sail area should be of this boat, but if I make it so that it's the same, so that I get the same number, 0.52, it turns out that I can put 149 square feet of sail area on my Wingmaran, and it will have the exact same number here as the 49er Skiff. A thing to note about all these numbers is you really get an advantage when your distance is, your distance arm is more of a factor than the weight difference. So remember, on the Monohull, you have a tiny little distance, 23, but you have a huge weight difference. This is not ideal. This creates a slow boat. The ideal situation is when you have a planing hull and then you have weight way over here. And this puts a big distance between your center of lift and your center of weight. So proas are very efficient at doing this. A planing proa would be even better. Nobody's ever made a planing proa except a couple that actually won Yellow Pages Endeavor. Look up that boat. That was a planing proa. The other one that's a planing proa is Sail Rocket 2. That's also a planing proa. They don't have foils for lift. They use foil to keep it from flipping over. Anyway, I haven't done a schematic diagram of those two boats yet, but I could do that in a different video. But the main point is, the reason this boat could be faster than this boat, and the Wingmaran could go actually more than 1.5 times the speed of the wind, is because they have the same distance, but this boat is lighter than this boat. So normally, you scale proportionally, but if you have the same distance as a boat that's heavy, but you make it lighter, it's gonna be faster. So that's why I have faith in the Wingmaran. I think it could go over 25 knots if I put a big enough sail on it. So that's what I'm working on. I think I'm gonna try to get a Hobie 14 sail, and at least that's 113 square feet. It's a whole lot better than the Sunfish sail, which is 75. So I'm going from 75 to 113 square feet, and the boat should still be very stable, and it should be very fast. One thing that is very interesting about both of these, the windsurfer and the kite surfer, is they can only go 1 times the speed of the wind. They cannot go, 1.5 times the speed of the wind like the 49er Skiff. However, both of these boats can go faster than the 49er Skiff. So why is that? Well, it turns out that the reason these can go faster is because they're more efficient at hydroplaning, but they are limited in their distance. The distance arm is 34 inches. So they're lightweight. They're really good at hydroplaning, but this distance is just too low. So that is what limits them to 1 times the speed of the wind. The interesting thing is, though, if you have 55 knots of wind, you can go 55 knots on a windsurfer or a kite surfer. It's just a weird thing that it has to do with the efficiency and the low drag. That's why they can attain those speeds. But if you were going to race around the buoys, the 49er Skiff would win.